This is the 2009 June Chemistry Regents Solutions. Here we go with number 51. All right. Sample of helium gas in a closed system with a movable piston. The volume of the gas sample is changed when both the temperature and pressure of the sample are increased. The table below shows the initial temperature, pressure, volume of the gas sample, as well as the final temperature and the pressure of the sample. So they give you a little blurb here. And some people like to read everything, and I suggest that could be a good strategy for yourself. Some people get lost in the shuffle, so to speak, with all this information, okay, and go right to the question. Okay, so it depends on the kind of person you are. I tend to read a little bit and go to the question because a lot of times they give you more information than necessary. But in any case, 51, in the space in your answer booklet, show a correct numerical setup for calculating the final volume of the gas sample. So we have initial temperature, initial pressure, initial volume. What's the new volume? So this is a classic, okay, combined gas law problem where we're using PV over T equals PV over T. And you really only have one gas law formula in this course, and that's it. And it's given to you in Table T if you forget. So let's go to Table T and then to the answer booklet to set this up. Here we are at Table T, and if you forget, there is your gas law, combined gas law formula. They even do P1, V1, T1 to show you that this is the pressure, volume, temperature variables in an initial, and this is the final. You certainly could switch, but I tend to think of this as the current condition, and this is the future. So make sure you put the variables together. Okay, so let's go to the answer booklet. It's really good practice to write the formula down before you plug in the values. In this question, they just want the setup, not the calculated result. So a little more easier, but nevertheless, you have to make sure you put the values in the right spot. So we have pressure, volume over temperature, and then pressure times volume over temperature. I call this the current state. You don't have to put the ones and twos if you don't have to, but essentially that's what you're doing. So current condition, and of course this is the future. Okay, so in any case, plugging this in, my current pressure or my initial pressure was 2.0 atm, and my volume was 500 milliliters. And the temperature, they were so nice to give it to us in Kelvin. If they didn't, you had to convert. Okay, is 200 Kelvin, right? Gas laws are based on, or this relationship, okay, on temperature, on pressure, or all the other variables are based on a Kelvin scale, a scale which we're starting from an absolute zero. Okay, any case, the new pressure is 7.0 atms. The new volume is what we're solving for, and of course the new temperature is 300 Kelvin. They didn't care if you put the points in, okay, they actually didn't care if you didn't put the units in. So you needed to have some 2.0 times 500 divided by 200 equals 7.0, so that's one way. Or you could have algebraically solved for V and said, okay, knowing your algebra, this goes to the bottom, 7.0, 300 goes to the top algebraically, and that would be your 200 below. And I'm purposely not writing the units just to show you don't have to have them, although I think you always should write your units, but hey, 2.0 and 500. And this is totally acceptable as well. All we did was put something on the top, on the bottom, something on the bottom, on the top, algebraically, because we multiplied both sides by 300 over 7.0 to cancel this side out, and of course add them to this side and solve for V. So clearly this one, or some combination where these numbers are on the right side, okay, are correct. That would give you a point. Number 52. Number 52 states, convert the final temperature of the helium gas sample to degrees Celsius. Okay, well the final, not something you calculated for, so the final temperature is 300 Kelvin, right from the graph, or the box, I should say, table. Okay, so 300 Kelvin, and we want to convert that to Celsius. All right, well, we know that there's a way to do this in table T. Let's go there. And in table T, they give us the formula for converting Kelvin to Celsius. So Celsius into Kelvin, and it's Kelvin equals Celsius plus 273. Notice there's no degree sign because the Kelvin scale uses the Celsius scale exactly. Okay, so the change in Kelvin is the same as the change in Celsius, but here's what we need. Let's go back to where we were. So Kelvin is equal to Celsius plus 273. They want to solve for Celsius, put the 300 for the Kelvin. So 300 equals my Celsius plus 273. Do your algebra. You're going to minus 273 this side, you minus 273 to this side, and you do your math, and you're going to get 27 degrees Celsius. And there you go, 27 degrees Celsius. That gets you your point. Number 53. Compare the total number of gas particles in the sample under the initial conditions to the total number of gas particles in the sample under final conditions. Okay, well, this is a pretty high-level question, but pressure, volume, and temperature, okay, are interrelated because the amount of particles are constant. If you keep temperature constant, you should know that pressure and volume are related inversely. It's called Boyle's law. And the reason why that works, for instance, if I have my piston, which is nothing more than basically a plunger in a column here, and I make the volume, the space that the gas is flying in, smaller. So if this piston comes down and makes the space smaller, obviously the gas particles have to be pushed into a tighter space, and therefore they're going to collide more often and the pressure increases. And that only works if you keep the number of particles constant. If we had a hole here, okay, and we push down, we'd be pushing, the higher pressure would escape into the other atmosphere and we would lose gas particles. So as volume decreases, the pressure inside here will remain the same, and that's how an air pump works. Okay? So in order for this to work, the particles have to be the same. If you look at another scenario like Charles' law, which is volume and temperature, we know that as temperature decreases, if you put some liquid nitrogen on a balloon, if you've seen that demonstration that we've done, okay, the volume goes down. You make the motion of molecules go slower because temperature is average kinetic energy, then they're going to take up less space. But that's, of course, if you have the same number of particles. So imagine if I've got a balloon filled up with a certain number of gas particles. These are my X's, bad X's. Okay? And if I make them colder, they don't need to separate. They'll actually condense into a liquid and maybe a solid. Okay? So they don't take up as much space, and this balloon would shrink, obviously, as you've seen the demonstration. But if I was to pump them with more gas molecules as I added the cold liquid nitrogen, the balloon wouldn't deflate. You have to keep the particles constant. And then for my honors and AP kids, anyone taking with a high-level course, you know that all the relations PV equals nRT. Okay, this is where PV over T came from this formula. Right? RT is a universal gas constant. If you haven't had any of this, just move on and move on to the next question. But for those that had, okay, if you notice something, PV over T algebraically equals NR. And that's the moles times the gas constant. So PV over T is equal to this constant. What's constant? Well, in part, moles. Okay, PV over T equals nRT. Well, PV over T could equal another PV over T in a different set of conditions. And that's where this formula was born from. So don't forget that this combined gas law is under the assumption that this moles are constant. It's the only way we can set them equal to each other. Again, if you didn't get that part in blue, that's okay. Number 53, let's go to the answer booklet. So I said the total number of gas particles is the same. Has to be for all the relationships that we studied. And that gives you a point. Number 54. So number 54 takes this relationship of molar mass, the mass per 1 mole of a substance, and their boiling points of 4 substances. Of course, these 4 substances are organic, right? They all have a carbon backbone, a chain, meth, eth, propbutane, and they're single bonded. Okay, so this is a homologous series, and as you studied, okay, as the homologous series, which is the same type of bonding, just adding more carbons, increases the attractive forces, which you should have learned in a higher level chemistry class, which are London forces, but in the Regents level, we call these weak forces, okay, steadily increase, which means that we need more heat to boil them. In any case, they want you to graph these. So number 54, if to earn 1 point, okay, they want an appropriate scale on the axis labeled boiling point. Now a scale, when you graph, represents one that is continuous and linear. No breaks. If you put a break here, you're going to get this wrong. It has to be continuous. Now appropriate means it shows, okay, a relationship or some kind of trend. So if you made your scale so small that your line is almost flat, you'd lose a point. So you don't have to use, it's good practice to use the entire graph if you can, but as long as you show the trend, you don't have to. And as long as your labeled scale is continuous with no breaks, you'll get the point. So for 54, there's my appropriate scale, 300. I did 50 per box, kind of makes sense. 1, 2, 3, 4, 5. Each box was 10, nice and easy. They normally give you a nice way to do that. Okay, no terrific math. And just showing you the plotted points, which is not what you were scored for in this question 54, but I'm showing you that my trend is easily being shown with my scale. So this gives me 1 point. Number 55. Number 55 states, on the same grid, plot the data from the data table, circle and connect the points. Okay, now just be careful, don't be lazy here. They give you plus or minus 0.3 of the grid space. Okay, so if you got a grid, okay, and you know, a third of the grid space. So if you're and that's a third now. So if you belong, I don't know, in this top third, and you are in the bottom third, you're going to lose points. Okay, so you got to be careful. You don't have to be dead on, but you got to be a third. I mean, a grid space is a box. Okay, so you've got to be within a third of where that point belongs. Okay, so I plotted my points, and again, your scale could look a little different than mine. You could have stretched it lower. Okay, you didn't have to use the entire. You should, but so this lines or these plots might be different. They asked you to circle them, okay, and connect them. However, interesting enough, they do not take any points if you don't. So we're going to follow directions, but they're not grading you if you don't. So let's connect the points, even though if you didn't, okay, and it's good to use as straight edge as possible because questions could be resulted from your lines here. They could be asking a question here. So use the end of your test booklet if you have to, because sometimes questions result, as we've seen in other tests. This will give you a 1. Okay. Oh, and don't connect from here all the way down to 0. Don't make that assumption. You have to start from the data. Okay. So number 55, you get that 1 point by plotting the points carefully. Okay, plus or minus a third of the grid space of where you belong. Someone's gonna do that. Someone's gonna watch and grade that on your Regents. Okay, maybe not me. Number 56. Based on the data in the table, state the relationship between a boiling point at 1 atmosphere and the molar mass for these 4 substances. Okay, well our graph, okay, is going upward. So as the molar mass increases, so does the boiling points, right? There it is, boiling points going up, and of course my molar mass increases. I might have got it backwards on the sheet, but that's how it works. Should put the boiling point on this side. Boiling point increases, the molar mass increases. And that's all you got to say. Number 56. So as the molar mass increases, the boiling point increases, or something along those lines that show that relationship. You could say it's a linear relationship. You can say it's directly proportional. Many ways to answer this, okay? That gives you the 1 point. Number 57. State in terms of intermolecular forces. They're asking you to answer using this concept, which is the forces of attraction between molecules. Why the boiling point of propane is lower than the boiling point of butane. The boiling point of propane is clearly lower than the boiling point of butane. Now, there's many ways you can answer this. You know it's organic. You know propane, okay, has 3 carbons, C3H8. And I know it's an ane, okay, because it ends in ane, and from table Q I get the general formula CnH2n plus 2. So I double my carbons and add 2 here. And of course butane is 4 carbons. Double the carbons, 8 plus 2, H is 10. Okay, now why does in terms of intermolecular attractions, well, you probably don't need these formulas, but hey, I'm just over teaching like I normally do. All right, but what do I know about these two? I know that higher the boiling point, okay, the stronger the intermolecular attractions, right? Their boiling is when the vapor pressure upward equals the atmospheric pressure, so their rate of evaporation goes up really high, fighting off the force of the atmospheric pressure. Now, if something boils at a higher temperature, that means it needs a lot more energy to separate the liquid molecules from themselves to evaporate. The reason why liquids don't all evaporate once you open them up to the atmospheric air is because they attract each other. Okay, they could be H-bond, they could be dipolar forces, weak forces, okay? But if you give them enough energy, they'll evaporate. And boiling is that maximum evaporation point at a particular pressure. So, higher the boiling point means that they must be holding on tighter. They're intermolecular attractions. You need more heat to overcome these attractions. So all you have to say is that in terms of intermolecular attractions, the boiling point of propane is lower because it has weaker attractive forces. It needs less energy to escape each other. Or you could say in terms of butane has stronger intermolecular forces. That's why it needs more energy to boil and thus has a higher boiling point. Okay, so I said the boiling point of propane is lower because it has weaker intermolecular attractions. You don't have to explain the details of the weaker just it has. Okay, things with boiling points that are high mean that they need a lot more energy to maximally evaporate against the atmospheric pressure, which means you need more energy to overcome your stronger attractions. Water resists evaporation. We put water and acetone on the table this year, and we watched acetone immediately evaporate. And water resists. Water has stronger intermolecular attractions. Now, you could word this so many different ways. You could say that butane has a higher boiling point because it has stronger. So you could phrase it the other way as long as the concept remains consistent. 57. Let me get that 1 point there. Yeehaw. Number 58. So explain in terms of particle arrangement why entropy decreases during this phase change. Notice I went right to the question, okay? Sometimes the blurb helps people, sometimes I go to the question. I'd have to say for the most part, my inference to tell kids is to read the question and go back to see what you need. I mean, I have a lot of students who get intimidated by all this information and get lost in what exactly they want, okay? Don't consider all of this, when you do that, unnecessary, okay? But see what they want first and go back into the problem. Any case, they want you to answer this question using particle arrangement. Why the entropy decreases. Now, entropy, of course, is chaos or disorder. Okay? Now, why is the disorder of the system decreasing? Or I could say another way, why is the order of the system increasing, right? If we know gases travel at speeds of hundreds of miles an hour And liquids, okay, have a lot of movement, but nowhere near the amount of kinetic energy gases have. They have to stay in their container. Gases don't, if it's an open system. So clearly, to go from a gas to a liquid, your amount of disorder is decreasing, so your entropy is decreasing. Well, why? Well, because liquids are more structured than gases, or gases are more chaotic than liquids. Many ways to explain that. But in terms of particle arrangement, how would I say that? I would say that the molecules of a liquid are arranged in a more structured, okay, form than the molecules of a gas. Liquid molecules are closer together, have stronger attractive forces, thus the particles, okay, are closer than a gas does. Many ways to say this. Number 58, let's go to the booklet. So I said H2O liquid molecules are more ordered than H2O gas molecules. And certainly you could say that H2O gas molecules are more disordered than H2O liquid molecules. But notice I'm using molecules. I'm talking about the particles somehow. Somehow in your question you have to phrase it in terms of the arrangement of particles. Okay? But there's so many different ways you could say this and get this question right, as long as you're on the same line of thinking. Number 59. Number 59 states, determine the total amount of heat released by 5 grams of water vapor during this phase change. So we're going from a gas to a liquid. I'm going to read the blurb up here just to make sure there's nothing here that there's something here that I might need. A pressure at 101 kilopascal, standard pressure, standard, and a temperature of 373. Okay, so well, isn't that that's 100 degrees Celsius, isn't it? Okay, is removed from a sample of water vapor, so removing heat from the gas, causing the sample to undergo a phase change. Okay, so we're going from gas to a liquid. Now, if we write a cooling curve, we can see a gas. Sometimes I say in class, gas, to show tremendous energy, so I'll say that again, gas! Okay, and then it becomes, there's a liquid phase here, and we have the gas going to a liquid, and we should know that the temperature stays constant. That's what they're alluding to here at 373, and we know that's really 100 degrees Celsius. Water boils at 100. And they're telling us the pressure, because we know that water can boil at all different types of temperatures. Okay, that would be really interesting of a question if they give you a different arrangement. But of course, they're giving you standard pressure. Water boils at 100, so they're giving you the hints. You're at a phase change. All these hints with this this physical change given to you here. All right, and the heat is given off. And from a gas to a liquid, condensation is exothermic. Our curve is going down. Okay, now, how do I measure the heat at a phase change? Well, some people remembered that Q is equal to mc change in T. This is a thermal equation given to you in reference table T. But they also give you Q equals mHF and Q equals mHV. And if you go to table T, let's do that. And here we are with table T at the bottom. The heat formulas are right here. Q equals mc change in T, Q equals mH of F. So what are these things? Well, HF is the heat of fusion. Fusion is a fancy word for melting. Okay? And vaporization is a fancy word for evaporation. Now, as we've talked about previously, this is a thermal equation when you want to measure the heat flow. Usually when you're at a pure phase. When you're at a pure phase, guess what you have? A temperature change. The graph that the cooling curve that I drew for you before on the other page looks like this. Gas, liquid, gas going to a liquid. When you need this equation, you have to have a temperature change. Pure liquid or pure gas. And you would need the specific heat, the ability to conduct heat or change its temperature. That's that factor here, specific heat capacity. You'd have to have it for that phase. We have it for the liquid phase. So a lot of our calorimetry problems, Q equals mc change in T, occur at the liquid phase because we have this C for the liquid. But at this phase change, there's no change in temperature. So I have to use one of the other two. And we use this one because we're going to use the constant for heat of vaporization. Now, heat of vaporization, by definition, is the amount of energy it takes for 1 gram of a liquid to become a gas at its phase change temperature. However, it's the same energy that's absorbed by a liquid to become a gas. It's the same energy for a gas molecule to lose to become a liquid. So this could be heat of condensation, heat of freezing. It doesn't matter. We use these constants when we don't have a change in temperature. So I can't use this formula, and I use the vaporization, constant to do that. And heat of vaporization is given to me in Table B. So Table B in all of its glory, it certainly was there a second ago. Oh, there we go. Maybe. There we go. Table B. All right. Table B right there, heat of fusion, heat of vaporization. Notice something. The heat of vaporization is so much more massive, I should say, correct English, than the heat of fusion. Why? Because going from a gas to a liquid has huge changes in potential energy, or even kinetic energy. Gases fly around at hundreds of miles an hour. Liquids do not have so. So that is the reason why it's so much bigger. But in any case, we need this value. So getting back to my question, so I'm going to use the equation for energy for this phase change, and I am going to get rid of the other ones. I'm not at freezing or melting, and I don't have a change in temperature, so I'm stuck with that. So here we go. Q equals mHV. Just going to rewrite it. It's good practice to write the formula that you need. And we're going to write, okay, the mass is 5 grams. And the heat of vaporization from Table B, 2260 joules per gram. 2260 joules per gram. And let's put this in our calculator. And we get 1130. Notice the grams will cancel, and you're left with joules. They did not ask for significant figures, and if they did, we would have 3 because ending zeros count when a decimal point is present. I don't consider this value for my significant figures because it's a constant. And we actually have 3 as a result. They didn't ask for units either. But remember, pay close attention to math problems. They could want the work and the answer. They could want significant figures. They could want units. Pay particular attention to your details here. Nothing that terrifically hard. Okay? So our answer is 11,300. Notice they put the joules in for you, and that would give you one correct answer. Number 60. So number 60's got a Voltaic cell. It's got a salt bridge. It is the battery. Okay, it's a battery. Also galvanic cell. So there's a little blurb here, but we'll go back to it later. I got my Voltaic cell, it's a battery, got my salt bridge to give me the overall reaction. What are they asking for? Okay, state the direction of electron flow through the wire between the electrodes. Man, they're giving you a lot of hints when the switch is closed. Okay, electron flow through the wire between the electrodes. I'm not saying anything else, but between the electrodes, between the wires. So you should not be mentioning these guys at all. I want between the magnesium to the copper to the magnesium. So when we deal with a voltaic cell or a battery, the absolute first step when you're working with these questions is determine who your anode is. And you've learned something. Anox, red cat. That's a nice mnemonic here. Okay, the one that is the anode is going to undergo oxidation, and the one that is the cathode is the place for reduction. So when I evaluate my battery, I've got to find my anode and cathode to start my analysis. So I start with my 2 metal electrodes, and I got to figure out which one is better at oxidizing. Now, if you haven't had much experience with the metals in lab, okay, you would need to go somewhere, but you may not if you've had experience with metals in the laboratory setting. If you had a activity series metals, you know that magnesium is more reactive than copper. Okay, that's why they make copper pipes with water. But if you didn't know, didn't have the experience, and you weren't sure and you're nervous, guess what? We have a place to go to evaluate, okay, how well each of these oxidizes, and that's table J. And here is table J up close and personal. Whoa, okay? Let's see here. We're dealing with metals, and we know the most active metals are the ones that love to, guess what? Lose electrons. Metals are big elements that have electrons very far away from their nucleus, so they tend to lose them and become positive. Losing electrons, Leo the lion, means you oxidize. Nonmetals tend to gain electrons. That's why they reduce. Grr. So metals, who's better at oxidizing? Magnesium or, okay, or copper. So here's magnesium, and copper is way below. There it is. So copper is so much better at oxidizing. Guess what? It's going to oxidize. Therefore, our mnemonic states, if it's going to oxidize, anox, that means it's the anode. So this is the anode, and copper must be the cathode. It's not as good as oxidizing, so reduction occurs there. Now, you should have learned in your classes, electrons always flow, no matter if it's a voltaic cell, electrolytic cell, any kind of electrochemical cell, electrons have to flow from the anode to the cathode once the switch is closed. Now, why? Well, oxidation, you guys should know, is a loss of electrons. Leo the lion. So magnesium, 0 goes to Mg plus 2, right? The half reaction. Mg0 goes to Mg plus 2 electrons. How do I know it's 2 electrons? Because a negative 2 and a plus 2 gives me 0 on both sides. Copper plus 2 is going to gain those 2 electrons that are sent through the wire and become copper solid. So this is reduction. Its charge is going down. It's gaining electrons. That's the Ger part. Okay, gaining electrons. Now, why am I doing this? Well, how can electrons flow? They can only flow by the substance giving off electrons to the one that is what? Gaining. You give gifts by giving, and someone has to accept. So the only way a gift can be given if the someone who brought the gift can give it. So it has to flow from the one that oxidizes, who gives the electrons, to the one who accepts. It can't go the other way. So it's always from the one that oxidizes to the one who reduces. It just doesn't make any sense otherwise. So the anode to the cathode, it would go left to right through the wire. So through the wire, electrons flow from the magnesium to the copper, from the anode to the cathode. You probably could say it goes left to right through the wire, from electrode to electrode. Many ways to say this, but definitely from the oxidation electrode to the electrode where a reduction occurs. Number 61. Number 61, state the purpose of the salt bridge in the cell. Okay, well, the classic question, why do we have a salt bridge? Okay, why do we even have a salt bridge? Well, we know that over time, okay, pieces of this magnesium, I'm just showing you how this gets eaten out, corrodes to make Mg plus 2. So as this solid metal, okay, and I have the half fraction here, becomes Mg plus 2 aqueous, this electrode gets smaller, but the amount of Mg plus 2 is increasing. How can electrons flow through the wire this way if this beaker gets positive? It'll never happen. Now on the opposite side, copper plus 2, now electrons are supposedly sent through the wire, okay, right here. Now the copper plus 2 is attracted to it and makes pure copper. That's what happens here. Over time, we're losing our positive copper plus 2 ion. So this beaker loses positive, so over time this beaker gets negative, right? If you lose your positives, and why would electrons flow towards something that's getting negative? Why would they leave something that's positive, which they're attracted to, and flow towards something that's negative? They won't. This battery would be dead. The battery does not work unless we have ions that can flow to counteract these increases or decreases of ions. So what the salt bridge does, it has positive and negative ions of a salt, and the positive, okay, the positive ion in this salt is going to come down here and move and replace the positives that are lost to keep this beaker from getting what? Negative. And the negative ion from the salt is going to migrate down over here and counteract the what? The increase in positives. So we're going to maintain electrical neutrality. We're going to keep this beaker from getting positive and this beaker from getting negative. And in fact, other ions can flow. So it allows the ions to flow. And in fact, if that's all you said, that's perfect. Okay, but it also, more importantly, I think, maintains electrical neutrality, keeps these beakers from gaining a charge so that the electrons can flow. Okay, so it allows for ions to flow. That's good enough. Or maintains electrical neutrality. What I cannot accept is it allow electrons to flow. And I have a lot of students who will put that there. And you don't understand. If electrons would flow through the salt bridge, why would they go through the conducting wire? Right? They would go to the path of least resistance. Of course, only ions flow. Okay, very important. Number 62. Explain in terms of what? They want you to answer this a certain way. In terms of copper ions and copper atoms, why the mass of the copper electrode increases. Okay, so I've kind of alluded this to already. Why does the copper mass increase? Because reduction is occurring. Look at your reactions. Copper plus 2 becomes copper solid. They're even telling you that. They're very nice. So over time, the copper plus 2 ions migrate to the electrons and get reduced and they produce solid copper. So plating occurs. And by the way, plating is always going to be reduction, and reduction's at the cathode. So copper ions are reduced to form solid copper atoms on the cathode, and that would give you your point. Certainly so many different ways to say that, but you had again say it in terms of what they wanted. You have to speak about the ions to the atoms. You should know copper atoms are solid, so plating was occurring, so ions became solid as they got reduced. So many different ways to explain that, but as long as you had the same way of saying it in terms of ions to atoms and solidifying onto the cathode, all could be correct. Number 63. State in terms the number of subatomic particles. In terms, they want you to answer in terms of subatomic particles, which we have 3 in this course: protons, neutrons, and electrons. One similarity and one difference between these isotopes of sulfur. Well, you should know iso means same, and they're all sulfur. And what makes sulfur special is its atomic number is 16. Now, if you didn't know that, you'd go to the reference table. It's the bottom number. They don't put the 16 here because it's implied. Why is it implied? Because we're using the S symbol, right? So if you have S, you don't need it. So they all have the same number of protons because they're all sulfur. What identifies the element is the proton number. Now, what's different about them? Because obviously there's some difference. There's a different number above here. That different number, okay, tells me the number of neutrons and protons, the mass number. So isotopes, if you should already know or should already know, exist because you have different number of neutrons for the same element. Okay, so what's similar? Protons are similar. They're all sulfur. What's different? They have different number of neutrons. And if you wanted to get that number, sulfur 32, and here's 16, you subtract that and you get 16 neutrons. If you do the others, and you don't have to do that, I'm just showing you. If I had sulfur 33 and I wanted neutrons, okay, 33 minus 16, that's 17 neutrons. So sulfur 33 has one more neutron. Now, why does this work? Because protons and neutrons combine to give the mass of the atom. All right, so isotopes are the same element, but a different form, a lighter or heavier form of the same element because they differ in their neutrons. So you had to state one similarity and one difference to get your 1 point. All atoms of the same element have the same number of protons, and isotopes differ by the number of neutrons. And that'd be enough to award yourself a point. Okay? Certainly you could say it differently. You could say all the different isotopes have different mass numbers, but this is by far the best answer. Protons are the same, neutrons are different. That's what this question was after. And you've seen this type of question before. They want you to know that isotopes are the same number of protons, different number of neutrons. That's all they were after, okay? And essentially, it's the same kind of question you would see in a multiple choice, except they give you a lot of information and want you to spell it out with words. Number 64. Number 64, in the space in your answer booklet, draw a Lewis dot diagram for an atom of sulfur 33. Okay, they want a Lewis dot diagram, which represents the valence electrons. So it doesn't matter if it's S33 or S32. It doesn't matter how many neutrons or they have. All of these would look the same because we're dealing with electrons. Okay, so we're not really drawing the nucleus, which has the different number of neutrons. We're just going to draw the electrons. And since these are all atoms, electrons equal the protons. However, we want an electron dot diagram, so we want to show the valence electrons, those electrons available for bonding. To draw a Lewis dot diagram, you have to understand how many electrons are available for bonding, and we're looking for the valence electrons. It has 6, these 2-8, these are core electrons. These are electrons that are not available for bonding. It's in group 16, that last number 6 is how many dots we need for sulfur. They didn't ask for an ion, which would need 2 electrons. It would have 8 filling its octet. We have to draw it 6 dots. So sulfur, we're going to draw the S, and then we're going to draw 6 dots. You can draw those 6 dots anywhere you'd like. Okay? So 1, 2, 3, 4, 5, and 6. So 6 dots is what you need. Again, as long as you got 6 dots, you're good. In truth, the symbol represents the 2-8, the core electrons, and the dots, okay, the dots represent the valence electrons. Okay, you don't need to know all of that, but essentially I need an S with 6 dots to get you your point. Pretty simple. Number 65. So number 65, in the space in your answer booklet, just show the numerical setup. They don't want the answer. Setup is good enough for calculating the atomic mass of sulfur. So this is called the weighted average problem. As you've already learned, I'm sure, to find the actual mass of what sulfur would be. You know, in the periodic table, we have something called decimal places for the mass. Example for sulfur, it's 32.065. Okay, oxygen 15.99. Why do we have these weird decimal places? Because what we're doing is we're going to average all of the isotopes for every single element, but we're going to use their weights, their percentages that exist in nature, like the question shows you. So we're going to do a weighted average and consider their percentages. Now, you should know that the most abundant isotope for sulfur is 32. That's why the average comes close or is closest to the most abundant isotope. And you probably can guess the most abundant isotope of oxygen is 16, since we can round off, it's closest to 16. So what we're going to do is we're going to take the atomic mass units, okay, I guess the empirical data that we get from a very precise lab, and we're going to find the percent of each one of these and add them together. So you take 31.93 and you're going to multiply that by 0.9493, right? Going to make that percentage. So moving that decimal place over 2 places. This one goes over 2 places. So this becomes multiplied by 0.0076. Move this one 2 places. This is times 0.0429. This goes over 2 places, so we get times 0.0002. Okay? Oh, we got too many zeros there. That didn't feel right to me either. Okay? People were screaming at me. It's wrong! Okay, 1. It is 3. Yeah, so here's the 1, 2, there's 3 zeros. Thank you for believing in me. So what you're going to do, party people, is you're going to multiply, and let's get rid of this. Ooh, yeah. Get rid of all of that. And what I'm going to get is I'm going to get these, oops, I always messed that up. Always get that value, whatever this answer is, I write it down, and then I add them up together. So what you're going to do is you're going to find the percent using the natural abundances of nature, find the percent of each of these, and then add up their values together. So I'll show you what that looks like, just to show the work. Okay, so here's what I did. I took the atomic masses that were given to me in the table right here, and I times them by the percentages, moving the decimal place over 2 places. And this is certainly one way you could do it. There's other ways to come up with the same answer. Okay, but essentially I'm multiplying my atomic mass by that fraction using the percentage. Like for instance, 94% is essentially 0.94. I come up with a number and I add those values together, and that would give me my point. Now, some people are still confused of weighted averages. You use weighted averages and real averages. Now, you can't take these 4 numbers and divide by 4. If you do that, if you take these 4 numbers and divide by 4, and some people did that, you'd be assuming that each one of these existed in nature equally. And you would say that 25% of the time. If you took 4 numbers, right? If you took 4 numbers and divide by 4, you'd be saying they're all equally weighted. And that's not the case. They're weighted far differently. Okay, notice sulfur, for the most part, is 32 point something. Why? Because the most abundant isotope, my friends in chemistry, in nature, is that one. And that's why we get closest to 32. Now, if you still don't quite understand this, let's take something a little bit easier. Carbon-12 and carbon-14 are isotopes. Now, if we want to average these together, a straight average, you guessed it, it'll be the number in between carbon-13. Right? Let's do a straight average. Okay? Now, you would take 12 plus 14 and divide by 2. And you guys all know that's 28 and divide by 2 and you get 13. Well, let's do it the weighted average problem to show you that when you do averages, you're really doing weighted averages, but you're keeping these equal abundances. So let's say I have 12, and if there's just 2 numbers, then each one exists 50% in nature, right? We're saying if there's 4 of these, and if we're not considering these abundances, we're saying each one is going to differ by 25% or the same. I have 2 numbers, so if I'm not considering the actual abundances and I divide by 2, what I'm really doing is saying that 50% is carbon-12. So if I times that by 0.5, hey, that gives me 6. If I take carbon-14 and times that by 0.5, because there's 2 numbers, I get 7. Half of 14 is 7. Then add the result, like we were doing here, I would come up with 13. So when you're averaging, you're still doing the same operation, but you are making every number equal weights, when in fact they don't. Okay? So number 65, that's how you would set it up, or something along those lines. And number 66. State one conclusion from Rutherford's experiment that contradicts one conclusion made by Thomson. Okay, so in this question, I went right to the question. I know there's a nice little blurb here. I'm going to go back in the blurb, but understand what they're asking. They want you to state one conclusion from Rutherford's experiment. Now, you should know Rutherford's experiment, the gold foil, right? He shot alpha particles through. Most of them went through the atom undeflected, showing that most of the atom was empty space. He also found some that did what? Deflected when they got close to something, or even repelled, bounced back almost. And that was very, very rare. So it showed him that the atom is mostly empty space, and that there's a small part of the overall atom where all the mass is located, okay, and it's a very dense, massive part, and that's the nucleus. He discovered a nucleus. But back to the question. State one conclusion from Rutherford experiments that contradicts one conclusion made by Thomson. Well, what did Thomson say? He said cathode rays deflected by electrical field. He suggested that cathode rays are composed of negatively charged particles found in all atoms. Okay. He concluded the atom was a positively charged sphere of uniform density. Whoa, that's a little bit different from what Rutherford found. Rutherford found it was not a uniform density. Most of all the mass was where? In the nucleus. That's why the alpha particles never hit anything except for very small occasions. So a conclusion by Rutherford that contradicts this uniform positive sphere density is the atom is mostly empty space. That contradicts his statement that there's a uniform density of positive charge. No, Rutherford found that all the positive charge was in a very small part, okay, volume of the nucleus, okay, or the atom, called the atomic nucleus. Remember that video I played? Yeah, okay. Number 67. Now, of course, you could say this other different ways, okay? An atom has a nucleus that's positively charged, and negatively charged particles are outside the positive nucleus, but you should really be hitting this nail on the head here, okay? Number 67. State one aspect of the modern model of the atom that agrees with the conclusion made by Thomson. Well, the modern model of the atom is the quantum model of the atom, electron cloud model, where we have a positive nucleus, and electrons do not exist in circular orbits. They exist in orbitals, okay, where electrons with a high probability are found, and they act as waves and particles. But the modern model considers electrons to be negatively charged, right? What did Thomson suggest? Okay, that the cathode rays deflected by electrical field, this suggested that cathode rays are composed of negatively charged particles. So we do consider electrons negatively charged. Also, what else did he say? He said negatively charged particles, he said the total negative charge of the atom was balanced by the positive charge. Well, we know that to be true today. An atom is electrically neutral because the protons, the positive value, equal the electrons. So a couple different ways to answer that. So I said electrons are negative. The modern model of the atom says electrons are negative, and certainly J.J. Thomson discovered that because his electrons, or his particles he found in a cathode ray, were attracted to or deflected toward a positive. Or an atom has equal amounts of positive and negative charge, and that would give you your point. Number 68, going right to the question. Identify one emission spontaneously released by a cobalt-60 nucleus. Okay, so without reading into any of this, I could look up table N, cobalt-60, let's go there. Table N lists all the different types of radioisotopes that they want to give you. It's selected, of course, not all of them. These are the select ones, whatever that means. Okay, and half-lives, how much time it takes for them to decay in half to something more stable. It's kind of decay mode, and its name. Well, cobalt-60 happens to be listed, and look at that. It gives off a B negative particle. It's decay mode, which, by the way, is a beta particle. If you don't know that, table O tells you. So table O tells you the symbol B negative is a beta particle. So you could say beta particle. Now you could also say gamma rays, because they said in the question, if you read into the blurb, a food irradiation facility replaces cobalt-60, a source of gamma rays. So gamma rays or beta particle is fine for the answer. So beta particle gamma ray is sufficient, and it gives you a point. Number 69. Number 69, determine the total number of years that elapse before an original cobalt-60 source in this facility must be replaced. Okay, so this is a half-life question. Okay, and we're going to need to know, if we're talking about how many total years it'll take before it has to be replaced. Now, there has to be something in my reading here that tells me when it has to be replaced. So I'm going to look into my value here, and it says, okay, when the radioactivity level falls to 1/8 of its initial level, okay, that's needs to be replaced. So a food facility replaces the cobalt-60 when it falls to 1/8 of its initial level. So what we're going to have to do here is make some space, and if I do just a very basic half-life problem, and I'm going to make a zero line up here. I have 0 half-lives, okay, 0 half-lives, and I have 0 time, and I have 100% of my sample, okay, which is the same thing as 1/1. After the first half-life, I have 1/2. The second half-life, okay, is 1/4. And the third half-life, a half of 1/4 is 1/8. All I did was take a half of 1 the first halving. Then I took a half of a half, which is a quarter. Then I took a half of an eighth. So I halved, okay, 3 times. 1, 2, 3. So clearly, what I just found out by doing this, it took 3 half-lives. Okay. Now, the question is, they want the total time it took for this sample to go 1/8 of its original. So I need to know where the half-life is. So I looked at table N for cobalt-60 for a half-life. And there I go. And cobalt-60 has a half-life of 5.271 years. Okay, let's go back to the problem. Okay, so if I know each half-life is approximately 5.3 years, okay, then each half-life is 5.3. I'm going to times that by 3, and 5.3 is 15, approximately 15.9 years it would take, right? So 3 half-lives. Now I did it by 3. You could have said, hey, 5.3. In the second half-life, you'd add another 5.3. So that'd be 10.6 at this point. And then you're going to add, another 5.3. Okay, and you get your 15.9. I don't care how you do it, but it took 3 half-lives to get to the 8th, and each half-life was 5.27. So if you were to take this raw number and times it by 3, okay, what you would get actually a 15.78. Okay, so I still believe you would accept this answer as well. No significant figures are necessary. So I was a little careless in my rounding here. They do show in the Regents form 15.78, but I believe you'd have some leeway into the 15.9 there. Because if you rounded to 16, we'd have to take it because there's no significant figures. So these numbers are essentially significantly the same. So any case, timesing your half-life by 3 gives you your answer. Next question. Before we go on to 70, number 69, we put our answer down. So that's 16 years approximately, or if you want to be more significant or more precise with your answer, I should say, 15.78. Okay, and that would give you your point. Number 70. Number 70 states, complete the nuclear equation in your answer booklet for the decay of cesium-137. Your response must include the symbol, the atomic number, the mass number of the missing particle. Okay, so we want the decay of cesium-137. Just to make sure nothing's going on, our little blurb here for these questions has nothing to do, well, it does have the nuclide 137 as a source of radiation for the prevention of food spoilage, and they don't say anything in what kind of radioactivity, so we're going to have to look that up if at all possible. So let's go to the booklet and see what they're giving us. I was just making sure there was no other hints listed here. Sometimes these radioisotopes are not listed in table N, and you got to see what kind of nuclide is given off. But I think this one is. In any case, go to answer booklet. So there is no need to look up what kind of decay mode or what kind of particle cesium gives off. It clearly gives off a beta particle. They're telling you. So they're going to say in this kind of natural transmutation where cesium is by itself, it gives off a beta particle. What is that element or that nuclide, okay, that's remaining? Okay, so very simple. All the numbers on the bottom on one side of an equation have to equal all the numbers on the bottom. So what number plus a -1 gives me a 55? Of course, it's 56. Okay, let's do the top numbers, the mass numbers. Same rule applies. Where we have conservation of charge in the bottom, now we have conservation of mass. What number plus 0 is 137? You put that in your calculator, and you get 137. Now, what element is atomic number 56? So you look on your reference table or your periodic table, and you'll see that that is barium. Don't trust me? Let me show you. Atomic number 56 is barium. Now, if you left it as cesium wrong, you have to have the right symbol here. So make sure when you do these very simple nuclear equations, you match up the right symbol. Okay? In any case. So this would earn you a point. Okay? Very simple stuff. I've had a lot of students who get this bottom number wrong. And of course get the wrong element wrong. So very careful, not a hard problem. Okay? Simple math. Law of conservation of charge and mass. Number 71. A soft drink bottling plant makes colorless, slightly acidic carbonated beverage called soda water. Okay, so got a little blurb here. I'm going to go right to the question. 71, explain why CO2 is released when a bottle of soda water is opened. Okay, well, it's released because of many different reasons, but if you look in your blurb, if you think you might need these hints, okay, during the production of the beverage, CO2 is dissolved in water at a pressure greater than 1 atmosphere. So when you open the bottle, you are lowering the pressure. And what you should know is gases are more soluble under a higher pressure. When you have a pressure that forces the gas into the liquid or keeps the gas from escaping because of the pressure on top, gases are more soluble under higher pressure. Open a soda bottle, you'll see the bubbles go to the top because of the lower pressure. So that's the explanation you have to say. The pressure is lowered, which lowers the solubility. So I wrote the pressure is lowered when you open the soda water and the solubility of gas decreases. They were just after, do you know that gases are less soluble under lower pressures? And something you already should have learned. And that's what that question was about, cloaked with its blurb and kind of its weird presentation. So that's all it was about. Number 72. Number 72 states, write the chemical name of the acid in soda water. So you have CO2, okay? And some people wrote carbon dioxide, and I believe that's acceptable, okay? But if you go to your reference table and you find table K, which is a list of common acids, you will see CO2 listed there, okay? And the best answer is carbonic acid. So exactly, CO2 or carbonic acid. I would accept carbon dioxide. And I believe a lot of teachers, again, it's not limited to just carbon dioxide, okay? Because the chemistry Regents scoring guidelines say acceptable responses include but not limited carbonic acid. So CO2 or carbon dioxide would also be acceptable. So this compound, okay, is what makes it acidic. And I'm sure your teacher, okay, might have blew into a methylene blue solution or some kind of indicator from table N. When they blew a straw, their CO2 made the color change happen because CO2 with water makes an acidic solution. Okay? And it's very important to understand that they wanted the name, not the chemical formula. So carbonic acid is what we're dealing with here. Okay? And that, of course, is essentially the answer. Now, you could have wrote CO2, a carbon dioxide. I would accept that. However, I get a lot of students in this question also want to write the chemical formula. They said the name. They had to give me the name. Read carefully. Number 73. State the relationship between the solubility of CO2 in water and the temperature of the aqueous solution. Okay, well, you should know that gases, okay, are less soluble, okay, under colder conditions. So if you go to table G, you'll see that there are curves that go downward as temperature increases. And you'll also see there are curves that go upward, meaning the solubility, this is the grams of the solute being dissolved, and this is the temperature. So as the temperature increases, the grams of solute decreases. Okay? And of course, this would be for a gas. Gases' solubility decrease with temperature because gases already have weak attractive forces. That's why they are gases. So because they have weak attractive forces, it doesn't take much energy to push them away from each other and escape into the atmosphere. Okay, now if you've forgotten about that, table G is your friend. All right, so notice most of these graphs are going up, and these are solids, solutes. Higher temperature, you can dissolve more of the solid, but notice there are 3 of these that go down. And you guessed it, these are my gases. Okay, so that's a little hint there table G gives you. So I write in the answer booklet, the solubility of CO2 decreases as the temperature increases, just like table G shows you, like for ammonia, which is a gas. Okay, number 74. So we've got some questions, a little blurb. If you notice the last group of questions we just went over, the questions really had really independent of the material given. There was obviously some parallels, but it's not reading comprehension. So we got bread making process, zymes is enzyme. They gave us some information. Balance the reaction. Okay, that causes bread dough to rise. Okay, using the smallest whole number coefficients. Okay, so I've got 6 carbons, and I have 2 carbons here and 1 carbon here. Okay, so I have to have 6 carbons on this side. All right, so because I have 2 places where there's carbon, I'm not going to attack it with the carbons yet. I know there's 6 C's. I'm going to start with the H's because H's are limited, okay, to 1 place here. All right, now if you notice, I have 12 H's on this side, and I have 6 H's, right? I have the 5 here and the 1. So I have 6 H's. So you notice to balance this chemical compound, or this reaction, so to speak, I need to have the same number and the same type of atoms on both sides. Atoms are not created, they're not destroyed, they're just rearranged. So if I have 12 H's on this side, I better have 12 H's on this side, or at least some common factor of them. So to do that, I'm going to put a 2 in front. This coefficient doubles my 6 H's to 12 H's, and I've just balanced my hydrogens. Now, by putting the 2 in front, that gives me 4 carbons. Now I need 2 more, right? Because I need a 6 on both sides. Well, that tells me I need a 2 here. You can throw a 2 there if you'd like, and that gives me my total number of carbons to be 6. So I have 6 carbons on both sides. Let's just make sure the oxygens work out. So there's 2 oxygens here, and 2 times 2 is 4. So 4 oxygens from the CO2 with the coefficient in front, and plus the 2 more here give me a total of 6 oxygens, and I have 6 oxygens. And you can put a 1 here. If you don't put a 1 there, certainly it's the same thing. So whole number coefficients, we've balanced the same number and same type of atom on both sides. There it is, number 75. Number 75, in the space in your answer booklet, draw a structural formula for the alcohol formed in this reaction. Let's go there. Hold on there, Mr. Grodsky. Alcohol form. What alcohol was formed? I'm going to have to go into my reading. And during the bread making process, glucose is converted to ethanol. So that's my alcohol. Now how do I know? Because it ends in OL. If you don't know, table R is your friend. Table R lists all the organic functional groups, and there's alcohol, and look, they give you an example of how to name it. So this OL is for the alcohol, and look at the general formula. R means the rest of an organic compound, some kind of carbon chain with an OH attached to it. So this is your R part. So we have a hydroxyl group attached to a carbon chain. The question is, what's the carbon chain look like? Well, the F tells me that there's 2 carbons. How do I know? Table P. So F means a prefix for 2 carbons, and because it was ethanol, right? It was ethanol. The AN means, really the E was there. You kind of crossed that out, so it's an ane. And ane means, as we've seen them before, single bonds. And there is ethane, okay? Single bonds between the carbons. So we have a 2-carbon system because it's eth. It's a single bond between the carbons because we have the ethane there. We don't write the E. The OL means we have an R attached to an OH. This R is the carbon chain, so let's put our OH there. And then of course we have to fill in the rest with H's. You don't have to put the H's in. The dashes are sufficient, but I am going to do that. Now don't do it halfway. If you do it like that, it'd be wrong. End them all if you're going to do it this way. And of course what I'm doing, the reason why that I knew, okay, that I had to add that many of those hydrogens, those dashes, is each carbon must make 4 bonds. 1, 2, 3, 4. 1, 2, 3, 4. I'm going to leave it like that, so that's sufficient as well. Carbon has 4 valence electrons, it must make 4 bonds, and there's your ethanol. Number 76. Number 76, state the effect of enzymase on the activation energy. So what is an enzymase? Let's go back. Okay, well, zymase is a enzyme produced by yeast. It is a catalyst. Okay, so what they're really saying is how does a catalyst affect the activation energy? And you should know a catalyst, okay, if I draw a potential energy curve, okay, changes the pathway so that the activation energy is lowered. And a lower activation energy speeds up their reaction. So they just want to know, be careful, how the zymase, which is a catalyst, affects the activation energy. It lowers it. It's a catalyst. So we say in number 76, zymase lowers the activation energy. That's simple. Number 77. So we've got another blurb here. In performing a titration, a student adds 3 drops of phenolphthalein to a flask containing 25.0 milliliters. Using a burette, the student slowly adds 0.15 molar, and the student determines the total volume of the base was 20.2. So number 77, we've got a titration problem. So I know that I'm going to be pulling this formula somewhere, somehow. But in this question, the concentration of the base used in the titration is expressed to what number of significant figures? So all they're saying to you, okay, is that, hey, how many significant figures is in this number? That's all. And you should know that 0.150. Leading zeros are never significant. They're just placeholders. Ending zeros are significant if a decimal point is present. So this has 3 significant figures. That's all they were asking. A little review of your significant figure rules. All non-zero numbers are significant. Okay, number 2, all sandwiched zeros are significant. So this would be 4 significant figures. Leading zeros are never significant. They help you get out to a low spot. So this has 1 significant figure. Ending zeros are significant only if a decimal point is present. So if I have 3,000, that's only 1 significant figure. It's a placeholder that helps me get out to the big numbers, just like these leading zeros are placeholders to get me out to the small number. Okay, to the ball game. Yeah, okay. Any case, if I put a point here, that means, oh, this has been measured. And now I have 1, 2, 3, 4. Okay, 4 significant figures. So because a decimal point is there, this ending zero counts. Number 77 is 3. So I put a 3 here. Number 78. Number 78 states, calculate the molarity of the HCl used in this titration. Your response must include both, and very careful, you see that, a numerical setup. So they want the work. And of course the answer. Okay, so we'll do this on the booklet. Okay, so this is a titration problem. They said it in the problem, and I'm going to use MV equals MV. And I know that formula is given to me in table T. And there it is. Molarity of the acid, volume of the acid equals the molarity of the base times the volume of the base. So I'm going to plug in my volume that's given to me in the problem and my molarity, my volume of the acid. I'm going to solve for the molarity of the acid. I'm going to plug in the molarity, the concentration of my base, and the volume. We should know our bases to be the hydroxide, the sodium hydroxide, and the hydrochloric acid. Pay close attention, though, that there is 1 H plus in this compound to 1 hydroxide. So there's nothing we have to do extra. But if there was an uneven number, you'd have to put the 1 with the double, put the 2 on the side of the equation. Just be aware of that. Always evaluate your acid and base. This is a monoacidic and monobasic in this case, which they are mostly. So they're going to give you a point for just plugging the values. And then you're going to solve for your unknown algebraically, and you get and you're going to get 0.121 and another point here. Notice the molarity on the milliliter is going to cancel to give you molarity. So all I did is just plugged in for a point, and then I just used my calculator and solved for it algebraically to get another point. Now, if you mixed up these numbers, you're going to get it wrong for the setup, but you'll get it right as long as your result here, you get a number consistent with your setup, so no double jeopardy. Okay, number 79. Okay, number 79, we have our final blurb. Okay, I'm going to go right to the question. Convert the mass of arsenic found in the body, okay, to grams. So after all of this, if you were to read it and your head would be spinning, all they want you to do is take the mass of arsenic and convert it to grams. Let's go find the mass of arsenic. Okay, so whoa, we have 5 milligrams of arsenic, and we want to convert that to grams. Now, it's a little bit of an unusual conversion because we don't usually use milligrams. Usually it's grams to kilograms. However, it's definitely doable. And I'll show you both ways that works. The first way, you should be using your units. So what I would do, let's get rid of some of this so we can see what we're doing. Okay, and make sure I'm in the right color here. And let's do red. So I'm going to start with what's given to me, 5 milligrams. So I'm going to use mg as my symbol there for milligrams. And I'm going to use the factor label method, dimensional analysis. I'm going to use my units. I don't care what you call it. So I want to get rid of magnesium, milligrams. So put milligrams on the bottom. And what do they want? They want to grams. The unit I want comes up top. So that way my milligram cancels. So I'm going to use my units to solve this answer. That's how I would always go about doing this. All right. Now the question is, what factors? How does one relate to the other? Well, milli means 1,000th, right? So a milli is 1,000th of a gram. So it takes 1,000 of them, right? 1,000 milligrams to equal 1 gram. Now, if you can't figure that out, think with me for a second. Who's got the bigger unit, grams or milligrams? Grams. So the bigger unit should always get the smaller numerical number. The smaller unit should get the bigger. All right. For instance, I'm a tall person if you don't know me. So if you take my body and you were to measure my length of my body to the side, say how many lengths of Grodsky does it take to measure the science wing? Because I'm a tall person, it doesn't take that many. So I'm a big unit, small number. Now if we take a smaller person, okay, it's because their unit is actually smaller. Measuring the same thing, it takes a lot more of them. So the smaller unit will take a lot more of them than to the bigger unit. So that's how one way to get that straight. Any case, as I didn't want to do that, let's go back down. Okay, sorry. So any case, the answer is going to be, okay, 5 divided by 1,000, which you put in your later of calcs is 0.005, or calculators, I should say. So 0.005 grams. Okay, now some people say, Mr. Grodsky, why don't you just move the decimal point? And you know, the decimal point movement is great, except inevitably someone's going to move it the wrong way. But if you have to do it this method, all right, King Henry died drinking cat milk. So keep doing this. King Henry died drinking cat milk is what I like to use because I just am tall and silly, I guess. So King Henry died drinking cat milk. Okay, I went from big to small. All right, kilo, hecta, deca, deci, centi, milli. So we're going to go from grams, which is what this would be, 1 gram would be here, and we're going to go from milligrams to grams. So we're going to get bigger, okay, so to speak. So if you notice, I'm starting in milligrams, okay, and I'm going to move my decimal place 1, 2, 3 places to get to this position. So my 5 becomes 1, 2, 3. Okay, so 1, 2, 3, and I get 1, 2, 3, and I get the 2 zeros in front. Okay, and of course your number should get smaller if your unit's getting bigger. Measuring in Grodsky's takes a lot less than measuring in someone who's shorter in length. Okay, so if you have to move the decimal place, move it so that you're moving the right number of lengths, and move it so that it's getting bigger or smaller according to the unit. In this case, we're going from a small unit to a bigger unit. The numerical answer has to go down. So there's your answer, number 79. Number 79, of course, is 0.005 grams. Number 80. Number 80. When heated, a 125 kilogram sample of arsenopyrite yields 67.5 kilograms of iron sulfide, iron 2 sulfide. Determine the total mass of arsenic produced in this reaction. This is a conservation of mass problem. If this is the fourth Regents you've done in the June series, you'd see that we probably have run into this. So what they're saying is I have a 125 gram sample, and the question really doesn't tell me much. Okay, let's see what other information they give me. They gave me the reaction, and I guess we're going to have to assume that every single piece of this sample reacts, okay, or decomposes, and we're producing 67.5 grams of the iron 2 sulfide. What's the arsenic? Now we can do a stoichiometry problem, as I've done in past videos, but we can clearly see that this is a conservation of mass problem. 125 grams of your reactants, you should have 125 grams of products. You're not going to lose any mass or create any mass, so conservation of mass. This is not a nuclear reaction. So all I'm going to do here to find my arsenic is 125 minus 67.5. And when we subtract, we get 57.5. And that's all that is. There's my answer. Didn't ask for sig figs, didn't ask for units. We just plug in the value from our calculator. Number 81. Number 81, write the formula for the compound produced when arsenic is heated rapidly in air. Okay. Well, let's think about this. I don't see arsenic being heated in air, but I believe in my blurb here, they're going to have to tell me something here. So we have arsenic is toxic, small amounts, the Bose. Okay, hold on. Gray arsenic is the density of this at SDP. When the arsenic is heated rapidly in air, arsenic 3 oxide is formed. Okay, so they want the chemical formula. Well, this Roman numeral 3 means arsenic is plus, argon. Arsenic is plus 3. Now, why would they tell me that? They tell me that because arsenic has two positive choices it can become. The Roman numeral system, okay, means that I'm dealing with arsenic plus 3. So arsenic oxide can take two different forms, one with the arsenic Roman numeral 3 number, or the arsenic plus 5. Okay? So the reasons why they tell me which one, if I had arsenic plus 5, when I crisscross to make my binary compound ends in IDE, okay, I would have arsenic 2O5. If I was dealing with arsenic 3, like the question asked, crisscrossing, I get AS2O3. So different chemical formulas, different, believe it or not, properties. Okay, so these are different arrangements of ions, okay, in this crystal. So obviously, you need to know which one, so the Roman numeral system helps us do that. So again, arsenic is plus 3. Oxygen, if you look at it on the reference table, it's negative 2. Crisscross and reduce to lowest terms, and you're going to get AS2O3. Just like that, AS2O3, and no phase necessary. Number 82. Number 82, explain in terms of the arrangement of atoms. Okay, so they want you to explain a certain way why the two forms of arsenic have different densities. So just based on the arrangement of atoms, oh gosh, okay, Christmas, okay, just by the arrangement of just the atoms. Why? Okay, well, we're going to have to go into our reading definitely here. Okay, when I go into my reading, let's clean up some of this. We say we have gray and we have blue. Gray arsenic has a density of 5.78. Let's see, yellow arsenic has a density of 1.97. Wow. Okay, they have two different forms. Okay, but one is more dense. Well, if they're both solids and one is more dense, I'm guessing that the gray arsenic packs its atoms in tighter spaces than the yellow. I'm not sure what else we could talk about here. There's a huge difference in density. So gray has its particles, its atoms packed in a smaller space. Okay, or arranged in a smaller space. We have to talk about its atoms, okay? All right, So I said in gray arsenic, the atoms are packed closer than they are in yellow arsenic. And you could say that many different ways. Yellow arsenic, okay, has its atoms farther apart than gray. Many ways to skin a cat. I go navel up. Number 83. Number 83 says calculate the percent composition by mass of arsenic in the compound, in that reactant. Don't want to say it again. Can't say it. Your response must include both a correct numerical setup and a calculator result. So a percent composition by mass is essentially a part over total times 100. Now the total that we're going to use, why not use 1 mole? 1 mole, or the molecular mass, or the formula mass. Let's go find the mass of 1 mole of the compound. Okay, so we go find that compound. It's Fe arsenic S. So we're going to find the mass per 1 mole. Why not? It can be, it's a percentage. You can pick any size you'd like. Since I know the mass of 1 mole and the part per 1 mole, let's do that. So I have 1 iron. So we're going to make something called the formula mass. 1 iron. 1 times the atomic mass of iron. Let's go to the periodic table. So the atomic mass of iron is 55.8. We can round off to the most common isotope, 56. Arsenic, our metalloid, you can round off to 75, and sulfur we can round off to 32. So I'm putting together my formula mass here. Oops. Not that. I'll be right with you. Sorry. Here we go. Putting together my formula mass here. 1 times 56 is 56, right? There's 1 of these per 1 mole. 1 arsenic, 1 times 75, and I'm getting these numbers right off the periodic table, the atomic mass. 1 times 32, and we add them together. And we get 163 grams per mole. So this is the mass per 1 mole, 163. And then we want what? The question stated percent by mass of, what was it again? Arsenic, percent by mass of arsenic. So in 1 mole of this, we've got 1 mole of arsenic, 75 grams. So that becomes my top number. And so 75 grams is 1 mole of arsenic. This is the mass of the entire compound. I times it by 100, and I get 46%. Okay, so this is 1 point for the work. Now, if your work is wrong, you'll get a 0 for it. But if your number is reflected of these wrong numbers, so if you put some wrong numbers in, you did your formula mass wrong, or you chose the wrong element or something, but your numbers are wrong. However, if your numbers are correctly calculated from what you have, they'll give you a point there. Okay, so that concludes the Part 2 free response B2C section of the June 2009 test. Hope you enjoyed. Keep it real. Rock on.